Hey everybody, welcome to the Austin Deep Learning Meetup. My name is John Ramey. Let's go ahead and get started. But before we do, I'm going to turn it over to our sponsor, Kung Fu AI, say a little bit about what they're up to.
Thank you, John. My name is Steven Strauss. I'm one of the co-founders of Kung Fu AI, and we're a sponsor of this meetup and a proud sponsor. Kung Fu AI is a professional services firm in the AI space, so we build custom solutions for companies. Some of our clients are up on the screen right now, and I was very excited to see Subu's name when the invitation came across, because we had a chance to meet 2 years ago, and I think you're in for a real treat because he's awesome. So we're always hiring. If anyone's interested in talking to us about what we're doing, we'd love to talk with you. And I appreciate, John, the opportunity to sponsor. So thank you so much.
Thanks, Steven. All right, so if this is your first time here, welcome. If not, it's good to see you again. So my name is John Ramey. I've been leading the meetup for a little over 3 years. Fun fact, actually, our initial host was Bitfusion here in town, and Subu was there right along with me. We, I think, hosted initially at Techstars in downtown, right above the speakeasy. That was crazy because at 7:30, that's when the music would come on, and we tried to get the meetup done before then. Anyway, welcome. Thank you for coming. In terms of the next few meetups, we actually have some pretty good topics that I'm very excited about. We have one person who is going to be giving a chat about TensorFlow 2.0, what all has changed. I've actually already seen his slides. I'm pretty excited about that topic because he's literally going to go through code like this is what TensorFlow 1 did, this is what 2.0 did. It's a pretty well structured talk. He's already got that going. We're going to schedule that for December or January. Got to get those details ironed out. We're also going to be doing a history of AI thing that I've been pretty passionate about for some time. We have a guy who's actually knows quite a bit about that very topic. We're potentially going to break that down into 2 individual talks, one maybe in January, one in February, or something along those lines. Basically, everything before the AI winter and everything after the AI winter. Clearly going for breadth, so we'll see how that goes in terms of time, but pretty excited about that topic. One more thing, if you do have a talk in mind, please reach out. We have very high quality talks here, very proud of that. We've been doing that for quite some time. Please reach out. We have a set of standard questions we'll ask you. Ultimately, we would love for you to give a talk, especially if you're building something or you want to represent your company. No sales pitches, please. However, if you want to plug your company and say, hey, we're hiring, please knock yourself out. But if you're working on something cool, let us know. So without further ado, I'm going to turn this over to Subu. He's going to be talking about FPGAs tonight, and I'm pretty excited about that. So welcome, Subu. Hello?
Hey guys, so actually glad to be back here. I don't think I'd actually presented at the Austin Deep Learning meetup ever. We just used to sponsor it like at one point, like a long time ago. So, but my name is Subu. I co-founded a company here in town called Bitfusion. We sold it to VMware a few months ago, and here I'm going to just talk a little bit about using FPGAs for doing deep learning inference and some of the merits of it, and I'm going to kind of talk about an application that I tried to build on top of FPGAs, and I've kind of open source the code base. I'm going to share the link to the code so you can play play with it or use it to your own needs. I also have Brian here. So Brian is very helpful. He works at Xilinx, so I use Xilinx FPGAs to do a bunch of these things. So he helped a lot, and some of the code that I'm using in the backend, I stole his code.
Yeah. So just, I gave a bunch of code to Subu, and he actually created a very interesting application with it. So I'm just here to add value, if I can, to the technical details of the backend code.
So how many of you here actually have heard FPGAs or know what FPGAs are? Okay, cool. So everybody knows what FPGAs are. So, again, I'm basically going to kind of go to the meat of it, right? If you look at the silicon alternatives for deep learning, you have, CPUs, GPUs, obviously, NVIDIA, and then you have FPGAs and ASICs. Unfortunately, there's been a lot of ASIC companies that are there, Graphcore, Wave Computing. I mean, there's like 50, 60 of them now. Again, none of them is really in the market yet, but I think they're going to kind of get there. If you kind of look at where the things play, if you look at training and inference, pretty much CPUs and GPUs are pretty good, right? It's very flexible, and GPUs are pretty fast. And then again, on the ASICs, the promise is, hey, some of the ASICs can do training, some of the ASICs can do inference as well. And these days, there's a lot of ASICs which can actually do even edge. There's a company in town called Mythic, which is using analog to do edge. And there's a lot of companies, which are doing edge with basically ASICs, especially because of the low power. The whole reason people kind of move from CPUs or GPUs to ASICs is when you basically deploy things on the edge, you want the power to be really, really low. And some of these guys are also putting this in data center because the biggest cost in a data center is cooling. So you don't want to basically, spend a lot of money on cooling. And FPGAs are kind of interesting. FPGAs are a bunch of, if I were to say, it's a bunch of fixed function units and muxes, connected to a really interesting backplane. So you can kind of reconfigure to do whatever you want, right? So you want to basically build, let's say, a voice recognition app. You can just make the FPGA morph into a voice recognition app. Or if you want to make an FPGA morph into, let's say, a video processing app, you can just make it morph into that. So you can pretty much wire it to do whatever you want because you have this sort of crossbar, fixed function units that are connected. So that's pretty much what FPGAs are. And there are two players who do FPGAs. So one is Xilinx and one is Altera, which is kind of owned by Intel now. And they're the two major players. And I use Xilinx for some other things, and I'll kind of tell you the trade-offs of why I use Xilinx in a little bit. But the primary value that FPGA provides are, one, you can basically put FPGAs as sort of bump in the wire. So you can, for example, if you have a CPU, you need to basically go through the networking and then to the CPU and then do some processing. Or even if you use GPUs, you need to go through the networking and then it needs to go to the CPU and then it needs to go to the GPU. So one of the things you can do with an FPGA is you can just connect an FPGA directly to the networking so that whenever a call comes in, it can literally go to the FPGA and process it. So because of that, FPGAs have been used a lot in financial trading for a long, long time. Sort of low latency trading where the latency is really critical. But it becomes a very interesting alternative even for inference because you could use an FPGA because of its low latency and the flexibility, right? So you can put any kind of neural network that you want on an FPGA. The biggest problem with FPGA that has been over the years is you got to write like hardware description language code. You got to write RTL, register transfer level, and everybody likes to write software. So nobody wants to write, HDL. And there were times where people could write System C and things like that. But it's still, who wants to write C, C++, right? Everybody wants to use a framework, use Keras, TensorFlow, and all these things, right? Those APIs were not really supported initially. But I think one of the things that has happened in the last year was FPGAs, both Xilinx and Intel, they started supporting higher level APIs to run directly on the FPGA so that you don't have to really pretty much know anything about the hardware details. So in fact, when I was building some of the applications that I built, I didn't have to really go into the detail of anything. Like literally, I never had to touch, the hardware description language ever. I was just pretty much using the APIs, and libraries were already built, so I was just using that. So that's the biggest change that has happened literally in the last year, and which is why I got really excited. And I had a lot of time to kill in the last few months. So I said, okay, let me just use this to do something interesting. So one of the things I used was a thing called Xilinx has this thing called Xilinx Vitis AI, which is basically very similar to NVIDIA's TensorRT. It basically has it has all the tool chain. You can take a model, quantize it, and then compile it to be able to run on an FPGA. And then you have a runtime so that you can run on an FPGA, right? And we'll go in the next few slides, we'll kind of go how it works. But the key thing to take here is you don't have to really know any of this stuff like that's here below. You can pretty much actually, you just need to run, you can just, just use the framework like Caffe, TensorFlow, MXNet, and things like that, right? And again, the link here, if you Google Xilinx Vitis AI, you should probably get a lot of interesting videos and stuff about what it is, which is going to explain it much better than what I do. But the link here is going to give you a good overview of what it is, right? If you guys are interested in going and developing on top of it. And you could also use the source code that I'm going to share, as a starting point. And I'm going to also put in a series of blog posts that I'm going to share, which you can probably use as a starting point to learn if you guys want to run your deep learning inference applications on an FPGA. So one thing is you don't run training on an FPGA, you only run inference because it's too expensive to run training on an FPGA. So I use, so good question. I used, Xilinx FPGAs, and even I think, some of the FPGAs are now available in the cloud. So I used, Amazon has something called F1 instances. So I used the F1 instances. So you could basically go and buy a board as well if you want. You could buy you could buy an embedded board, you have a Zinc board, a Z board, which is actually pretty inexpensive. Or you could just use it on Amazon. Amazon basically, it's probably the best way to start using, running things on FPGA. Yeah, so the cost, it's the F1 and F2 instances. So the cost of that is actually pretty expensive. I think it's like $1.65. Yeah, it's $1.65. So I have actually 10 nodes running. So I'm paying $1.65 for every hour. That thing. So the way it works is, right, you basically take a trained model and then you run it through a compiler. And then once you run it through a compiler, it gets automatically programmed on an FPGA. You sort of put in a real DNN processor on an FPGA. As I said, an FPGA is a bunch of fixed function units connected with muxes, so with a crossbar. So you can pretty much create whatever you want in hardware, but through software interfaces. And this tool flow that is there, hopefully you guys can see it. I can't see it, it's too small for me from here. So there's basically 4 steps. So you basically take a deep neural network and you run it through an optimizer. And what it really does is it prunes the network. It basically removes all the redundant nodes in the network, and it basically sort of think of it as like a compressed network, right? That way you have to do less computations. And the next step that you do is you take the same network and you can kind of run it through a quantizer. And what a quantizer really does is, if you have FP32, floating point 32, it can basically quantize it to either int 8 or int 6 or int 4, right? So sometimes you might say, I don't need a lot of accuracy. I can trade off on the accuracy, so I don't need that many bits. So all these basically now have tool flows. It's all like Python scripts that you can run, and then you basically take it and run it through a compiler, which is literally going to kind of generate the DPU instructions, which is sort of like, think of it as running like, for example, when you're running through TensorRT flow, you basically run it through a TensorRT, compiler, and it's going to give you the most optimal code base to run it on an NVIDIA GPU. Very similar to that here. And then you literally take that and then you run your inference, program on top of it, right? So you can run it either on a Zinc or an Alveo or any of those things. And I'm going to probably ask, Brian to add a few things on this here.
Yeah, sure. I'll add a little bit of color to this. So the first step that Subbu mentioned, the optimizer, this is also commonly referred to as pruning. This is an optional step. You don't have to do it. And what it does is it's like, it's done while you're training the model. Well, after you train it, then you continue in the training flow. And if you can achieve the same accuracy by cutting out layers in the graph, cutting out computation, you're solving the same problem with fewer compute, like less work. So it's better overall for you. Quantization, we're converting the model to achieve the same result with integers instead of floating point numbers. So by doing that, you can squeeze a lot more into a singular device. So that's the motivation for it. There's other motivations too, like it's lower power. So it's just it's a good thing to do for inference, not for training, because for training you need really fine granularity to each step of gradient descent. You want to fine tune by just a little bit, right? Increment your weights. And then the compiler is a step to basically generate microcode for the accelerator in the device. That's all I have.
And so again, the reason I kind of gave you this kind of background is, so we're not going to use any of these steps 1, 2, and 3. We're not going to actually use this. We're going to basically, as I mentioned, those things are sort of can be abstracted, and we're going to mostly use step 4. So I'm going to take a pre-existing model that in fact Brian built, and I'm going to use it to do face detection. And later on, we can basically see how we can scale it to do any application that you want. Sort of, you can build your own FPGA as a service application, or you can use inference as a service application. So this is basically a very simple application. I'm just putting the architecture here. It's a face detection using an FPGA. So in the backend, it's literally a Python a Flask backend, which is basically a REST server running on a container, and it's literally serving the inference. It's basically taking these models that already went through steps 1, 2, 3 here, and we generated a REST API, and that's kind of being served. And then we have a client which kind of keeps talking to this, right? So this is what we initially built, right? And if you see, the biggest challenge with this is this works in a single tenant environment. Let's say if you have, let's say 5 users, 10 users, maybe 20 people actually talking to this backend. But what happens when you start talking to, when you have like hundreds of people, right? So talking to it, it just will start barfing. And in fact, if you actually see this next slide, and that's what I was going to actually talk about, using FPGAs for doing inference, but also how do you use Kubernetes to scale out so you can actually get a low latency. So here, if you actually see this example here on the left, I have a bunch of video frames that are being emulated. So I've kind of replicated a bunch of videos as if you're kind of actually creating, if you see this number, it's basically generating like, 24, 25, 30 videos that are coming in. In this side, it's like the same kind of videos that are coming in. And if you see this thing, I don't know if you can see it here, the first video is kind of actually becoming very choppy. I don't know if you see on the left, without scale out, it's very choppy. And on the right, if you see, the video is very smooth. And the reason it's getting very smooth is because on one side, we are running things on an FPGA, but on the other side, what we're doing is we're also scaling it out. So through a combination of both running it on an accelerated device and scaling it out, you get this really smooth way of processing. And here the example is basically doing face detection. But now imagine you can do the same with other kind of applications as well, right? So that's kind of the main point here as to what I'm going to go through. So what I'm going to go through is take a simple backend that we kind of actually see here, which is like a face detection backend, which is running really inference on an FPGA, and then take the front end and kind of scale the backend using Kubernetes horizontally, and I'll kind of go through a reference architecture that I used, and you guys could use it for your own serving apps that you guys have as well. So before I actually do this, right? So if you guys can actually take your phones and go to that URL, I'm going to kind of show you a live demo of what's really happening, and then we'll kind of go back to. So 1 second, I'm sorry, 1 second. My screen kind of I know, sorry man, yeah. Okay, so now it'll happen immediately. Oh, sorry. Okay, sorry. So let me know when you guys have it. So you will basically do the same thing here. Everybody has it? Alright, so now let's actually see everybody on the screen. Alright, so now imagine, as more people kind of start coming in, if we did not actually, kind of scale out, of course there's not a lot of people. I was hoping there'll be 64 people here today. So it's a lot of backend, but you kind of get the idea, so what this app is going to be, right? So depending on the number of people coming in, it kind of like, kind of scale out the number of nodes automatically. And I'll kind of go through, how this whole application is being built. So this sort of shows the workflow architecture. So on the left, you see a bunch of clients, and that is basically a simple Python server for serving the HTML and JS. On the right, I have an admin, which is kind of the page that you guys saw, which was all the faces that we were seeing, that you guys were seeing, and that is again a Python server serving an HTML and JS. And if you see, there's a WebSocket server that is there, which is basically a Node.js WebSocket server that is literally used to transmit images from the client, the application that you guys ran on your phones and on your phone browser and the admin, so that we can basically talk back and forth between the backend. And then the next important piece here in this architecture is the CAM worker, which is basically if you remember a few screens ago, I was showing you this backend REST API, which was really running on the FPGA. So this CAM worker is the one that's running on an FPGA. And then there's a Redis, a PubSub, and a queue that is there. And the reason I have this Redis queue is because imagine, so the way this whole architecture is built is, so as you guys basically, open up your phones and, the frame starts, coming in from the webcam stream, the frame gets passed through the WebSocket server and it basically goes into a queue in Redis. So all the things basically go into this queue, and then the CAM worker starts picking things from the queue. So, and the reason a single CAM worker is not sufficient is because if the queue kind of fills up and if the CAM worker cannot process fast enough, then you basically see a backlog, and that was the reason you kind of saw on the left, the queue was kind of, the frames were kind of getting choppy, right? So one of the things that we have done here is we kind of actually scale the CAM worker using Kubernetes to horizontally scale it. So we basically have as many CAM workers as we want, and right now I've kind of auto-scaled it. I've kind of hard-coded it, but sort of auto-scaled it. But you could also auto-scale it based on the load. And pretty much, what it really does is, as the queue kind of backs up, it spins up a new CAM worker. As the queue kind of backs up, it spins up a new CAM worker. So that way you can horizontally scale this, and then as the load reduces, you can kind of automatically scale down, right? So that's kind of the architecture here. And again, the whole source code, I'm going to share the link to it. It's kind of all public. And to be honest, right, so you could take this whole architecture and use the Redis queue and the PubSub and the WebSocket server, but pretty much replace everything else with whatever you guys have, right? So you could use a CAM worker that I have, and then you could replace it with your own application that is there. So there's a bunch of applications, and I'm going to share a link where you can find a bunch of interesting applications that are going to be there, and you could just replace it whatever you want there. And this kind of provides a framework, and to be honest, you could use it with FPGA, but you could also use it with GPUs and CPUs as well, right? There's nothing stopping you guys from using it. So think of it as like a horizontally scalable inference server, but using FPGAs in the backend to do low latency. And because it's horizontally scaling, it's always going to be kind of high throughput, low latency, because the queue is always going to be making sure it's being served. So this, picture kind of shows the system architecture. So you basically have the master, and I'm using a device plugin, a Xilinx device plugin that was already there, very similar to the NVIDIA device plugin. and it basically has a CPU-only node, which has 3 pods running. The CAM server, which is serving the JS and the HTML for the admin and the client, and the WebSocket server, which is really, passing the images and stuff back and forth. And then the Redis pops up, which is basically managing the queue, and as and when the backend processes a face, it sends the coordinate of the face into the queue or into the publishes it, and then the what do you call the WebSocket server kind of subscribe to it. They basically take it and basically service it back to the CAM server. And then on this side, I have a CAM worker, a container, which is really running the backend. The backend is the face reduction that we saw, and what all that really does is it takes the model that was already compiled, and it's running a Python Flask-based API server, and it's whenever an image comes in, it sends a coordinate back, right? So imagine you could replace that with whatever application that you have. You could have a face reduction application, or you could have a speech synthesizer. You could have some security applications, or whatever backend you have. You could just, you could pretty much, you should be able to use it, as it is, right? So and in this slide, it's kind of too small, and I'll probably publish these slides also so you guys have it. It kind of shows the workflow that I just talked, right? I didn't realize that things are going to be too small to read here. So, basically, I won't actually, go through this sequence diagram, but pretty much, what really the sequence diagram does is it kind of walks through this workflow that I just talked about, like, as the CAM server goes, kind of serves the pages, and the clients send the images to the WebSocket server. It goes in the queue, and the CAM worker takes every image, run through the neural network, right, the inference, and kind of returns the coordinates back, and the coordinates gets published, and it gets picked up, and it gets rendered back in both the client as well as in the admin, so that you can actually see it, right? That happens like again and again and again. And in the back end, the CAM worker is just horizontally being scaled. And in here, in fact, to be honest, even the web application side, the container, the WebSocket and the Redis container, they are also actually, potentially you could horizontally scale them as well. But I'm not really scaling it in the, in the application that I have right now, right? So. The full source code is here. I'm just going to leave it for a little bit in case anybody wants to take a picture or something. So you want to actually pull up the source code. So yeah, it's basically, you should be able to download the source code, and it has full instructions on how to, I'm using Terraform to set up the Kubernetes cluster, and I'm using Packer for the AMI images. But you should be able to use it to run it on-premise as well if you guys want to run it on-premise. How many of you guys here have like FPGAs on-premise? I'm just curious. Like anybody has in the data center? Oh, cool. Where do you work? Okay, so no wonder. All right. Okay. Have you guys, anybody here used FPGAs? Okay. I'm just curious, what did you use it for?
Medical imaging device.
Oh, cool. Okay. What about you? You use FPGAs too? Oh, experimenting. Okay. What do you experiment with? Okay, cool. All right, awesome. I was just curious, because like, a lot of these things actually are kind of like just came out in the last year. So always curious, like who all actually played with an FPGAs, right? So, and this is basically the whole source code, right? So this has instructions on how you can actually set up on your Mac, and how it basically has some setup instructions for so you basically set up an S3 bucket for your Terraform, and then just bring up your Terraform, uses kubectl, and then this has some instructions on how you build your Docker images. There's basically a container registry that's being run as well, and then it has an instructions on how to basically set up your Packer AMI that you have, but most of these are kind of public as well, so you can you can probably use it and use it as a starting point. Yeah. No, the packer is just for the AMI. So it's just an AMI building. I'm just using it for AMI building, that's it. Because the AMI has to have certain custom, like tools and everything that's installed. So you can't just use any AMI that you have because it needs the device driver, it needs a runtime and all those things. So it's just like the base AMI for your communities. That's pretty much it, yeah. And basically, if you basically use your own AMI, this won't work. Right, so you have to basically use this AMI that is there. But if you kind of walk through these steps, it should pretty much be straightforward. And I actually have a blog post also on this. I haven't actually published it yet, but as soon as I publish it, I'll send you guys a link. So you should be able to walk through the whole steps. So which is like it basically has like step-by-step instructions on how you need to do everything. Literally, like you should be able to like walk through this, and it should hopefully work. It'll at least work on my machine. So. Okay.
So just to clarify,
Yeah.
You have Kubernetes is that to corral all the container instances, but you only have one FPGA in that example, right?
No, I have actually. So I was actually no, I don't. I have a lot.
Container would have access to one FPGA.
Each container will have access to one FPGA. Exactly. This is basically my my thing, right? So basically, I have I think I have like this must be 9. FPGA instances that are basically running, but I could pretty much use, so there's an F1 8x large as well, or an F1 16x large, which basically has 8 FPGAs on a single instance.
Okay.
I could use that. The reason I did not use that is because the backend application, the REST application that I have, it is written to use only one FPGA. So I didn't want to use otherwise I would have to basically spin up like 8 containers on the same node, right? So I could do it that way too. I could basically have 8 pods spinning up on the same F1 8x node. That way each one is using one FPGA, and then I could kind of horizontally scale that as well if I want. But I did not do that. I just used the F1 2x large and just horizontally scaled it.
How fast would it scale if you just go viral and you need more? I understand the cloud part would work well, but the FPGA, how fast can you get the FPGAs?
Well, there's nothing. It's really bringing up the machine, right? That's pretty much it, right? So it's the FPGA is just a device that's there. So it's.
You need to have them. I don't know too much about it, but you need to have them populated. This kind of.
Yeah, that is very fast. The program, the FPGA is actually pretty instantaneous. Like it's I don't know how fast it is. It's exactly, yeah.
It's only a one-time build. You just do it once and then you leave it programmed forever. And then you just keep doing it again and again.
No, I know, but then that means you have to have that capacity to serve.
So you don't have to, right? So you don't have to. That's what I'm saying. So it's only a millisecond to basically, a few milliseconds to program the FPGA. Right? So you could basically have it in such a way. And AWS has a whole another set of tutorial on how to program an FPGA, and they have something called AFI. So if you actually Google AWS AFI F1, so there's basically a whole a tool flow on how you can program an FPGA, and you could pretty much actually write some tooling which kind of automatically on the fly, as and when an instance comes up, you could basically have some tooling to automatically program the FPGA and then bring up a container. So but this does not do that. But theoretically, there's nothing stopping you from doing that, and it should be like, it should be milliseconds to bring that up.
You just use it and then return it so you can charge.
Exactly. As I said, this is like, I'm going to continue improving this over time, and my goal is to basically improve it and make it in such a way that you probably at some point don't have to worry about any of this stuff. So you could just sort of like Lambda with FPGAs, right? That's kind of what I'm thinking here, right? So think of this as like the starting point for that.
So there's no way to use a Lambda right now with it?
No. There's no way to function F1 FPGAs on AWS today. Yeah. Actually, it's actually the same overhead actually even for a CPU instance too. How much of a time it takes to bring up a CPU instance, it's the same amount of time you're going to take to bring up an FPGA instance too. It's not like, it's not much difference except the programmability piece. That's the only piece that's there. So the way you actually measure it is by 2 ways, okay? So you could potentially run this on a CPU instance as well, And what you do is, for example, you could, so when a face comes, right? So there's in the same face app, there's basically like a queue time that is basically going to be there, and that queue will be the time that you. There's a queue time on this side, and there's another time on this side. I don't know if you guys see it. So I'm going to show you a little bit. There's a D. So this D you can basically see, and basically spin up something on a CPU instance, spin up something on an FPGA instance, and basically see if this D is better on an FPGA versus a CPU. And that's one way you could benchmark it. I mean, using this application, right? But yeah, it's basically like the input frame. How long does it take to return the rectangle? Does it answer your question? Yeah. Okay. So that's pretty much it, and I want to kind of show a little bit of so this is basically these are the FPGA nodes that I have. This is basically a standard thing, right? So and I'm basically using sort of auto scaling groups. I have a couple of so I have these two groups that I have, right? So I could basically go on, because I'm paying a lot of money for this thing now. So I'm basically going to go and basically reduce it to like one instance. So, I'm basically going to reduce it. So you could use this framework to do whatever application that you have in your mind. So it should automatically scale down automatically. And all you have to really do is change hopefully it works. Yep, it's right, like shutting down, right? Yeah, so and the whole idea here is, right, so you should be able to kind of actually think of this as a system architecture, and whatever I have on the red box, you could pretty much use the same container and go inside the container and change the face detection application to do whatever you want in the backend, right? So that's so you should be able to use it, and love to hear your thoughts after you guys try this out, and hopefully it works for you guys too on your machines. And I've just put both our emails here, so if you guys have any questions, feel free to reach out to us.
I just want to say that I'm pretty impressed with what he threw together here, because I just threw him one piece of code. I just threw the back end. So like once the image comes into the Flash server, I call one API, XGNN execute, and so that sends the image, the NumPy array, down to the FPGA and back. And so I gave him that as a starting point, and he built out the whole horizontal scaling, the Redis data store in the middle. So I just want to say it's pretty cool what he did.
What are your thoughts in terms of cloud independence? Like, you want to move this to Azure? It's taking a lot of work.
No, it's just a Terraform to bring up the Kubernetes cluster, and yeah, that should not actually be a lot of work at all. In fact, Azure doesn't have I think it has Intel FPGAs. I kind of I played with both Intel and a long time ago. I just think they don't have like the NVIDIA TensorRT style thing yet. It's one of the reasons I kind of stuck with this. But yeah, you should be able to buy a bunch of FPGA servers or buy cards, put it on your home, and just run this. It should theoretically work. Yeah. And that's one of the reasons I basically picked Kubernetes for this. That way you don't have to, and that's the reason I picked Terraform for this. That way you don't have to really, like initially I was thinking of using COPS, but then use Terraform because it just allows you to, move from one cloud to another or one data center to another. And even embedded actually. That's one of the things I want actually, make this is to be able to run this on an embedded thing. Imagine you have a swarm of all these, like either FPGAs or even ASICs, right? So all these things are running, and I should be able to sort of have this as lambda functions, and bam, just horizontally scales, right? So.
So one question about device plugin. Did you just download it from Zabbix? Is there something Zabbix provides device plugin for Kubernetes?
Yeah, actually, yeah, it's actually again. So if you Google, again, I'm sorry I didn't have the link handy. So So this is the one, right? So if you basically, there's a device plugin that Xilinx provides, very similar to the NVIDIA device plugin that you have. So it actually reduces a lot of work. Initially, had to do a lot of hacking to get this thing working, but then, yeah, I actually accidentally discovered this, that it existed. Yeah. I actually, like, in fact, at one point, even at BitFusion, we were actually trying to build our own device plugins for, even NVIDIA as well as, Xilinx at one point when we were working on FPGAs. Yeah, I'm glad actually this basically reduces the amount of work that somebody has to really do. Yeah, what I did was I basically used what Brian had. He basically had the face detection application. He basically built the neural network. I literally used this thing. So I basically built all the other infrastructure tooling to kind of horizontally scale this and vertically scale this. Exactly. Yeah. Yeah. So you could basically use whatever, anything you want, right? It's literally a REST API that you basically know. So in fact, I have an example. Let's see if I can pull this. I don't know why it's like my screen is crashing. Okay, works. Okay, yeah. So it's basically like an API like this. That's what he gave, right? So. Sure.
So the FPGAs, how does like say you have a really large FPGA, can you run multiple processes at the same time with a service, or is it just one in, one out?
Yeah. Actually, you can actually run multi processes in the same FPGA. In fact, there's some actually tools that that I think even Xilinx has, which kind of actually does that. It's like Neptune or one of those things. Ashish, do you know anything that's right now it's public?
Equally public.
Yeah.
With the license.
Yeah. So, yeah. Actually, in fact, you could even actually you could basically run like because you can try to use FPGAs 100% utilized. And that's actually one of the coolest things about actually a field program body, right? So you can pretty much use every piece of the hardware as much as you want. But I did not do that here though. In this application, I didn't use that. So I only use one process per FPGA.
Subbu, thank you so much. That was actually, I learned quite a bit. So typically we go right across the street to CU29. It's a cocktail bar if you've never been. It's literally right out there. Usually some pretty good discussion, 10, 15, 20 people do show up, and we typically, conversations with the speaker or what have you, carry over to there. Really good conversations that have developed, made a lot of friends over there. So please join us, and if this is your first time, thank you for coming.
He left the whole Backend industry, right?
Nearby here? No, I'm in 183. I know people. I'm a Messi. I must be an
Asking for
No, I know it's very important.
so that you cannot use that's one of the reasons I basically have honest, that queue cannot be solved, right? There are only two bottlenecks out there, right? So the biggest bottleneck that you have is the front end, where you cannot handle enough clients. Or the second bottleneck is you don't have enough backend workers to send another product. So the queue just gets used. The queue is pretty dumb. All it really does is I'm just putting in images in the queue, and I'm just taking an image. The camera is taking images. This guy might, if this camera is taking